So, good morning, afternoon, evening, all wherever you are. And welcome to the Spring 2021 edition of Intro to Deep Learning. The title here you will see is Neural Networks. These days, when you speak of deep learning, you're only speaking of neural networks. So before we begin, and the reason I'm beginning a couple of minutes early, a little bit of logistics first. Before anything happens, I'd like to introduce all of my TAs. These are the superheroes who are going to be running the show. And not all of them are here because some of them have classes at the same time as this one, but several of them are here. And so maybe, I'm not sure how, if you guys can see their faces, but I'd like all of them to raise their hands and I don't know. Does anybody know how we can make sure that your face actually shows up on the little picture? So, all right, let me see. I'm going to go from the top. I am going to try. Harshwan, wave your hand. Can you?
Yep. Can you see me? No, I think.
So, all right, guys. So here's what you do. My TAs, please just say your name and wave your hand, and hopefully the fact that you're speaking makes your face show up on the little screen.
Okay, can you see me?
Yeah. So just say your names.
Oh yeah. Hi guys, my name is Hao Xuan, and I'm currently located in China. So I will majorly help those who are in China, India time zones. But for the people from Pittsburgh and other places, you are welcome to contact me via Piazza or go to the office hours. And so it's very nice to have you with us, and happy deep learning. Thank you.
Thank you. So Vaidehi.
Yeah, hi everyone. I'm Vaidehi and I'm currently located in. So I'll be your TA for this semester, and good luck to all of you. And it's nice to meet all of you.
Anurag.
Hello, everyone. I'm Anurag. You probably already saw me in lecture 0. Great to see everyone in lecture. Hope you have a good day.
Yeah, David. David, you here? So David's muted. Noor.
Hi everyone, my name is Noor. I'm from the CMU Qatar campus, so I'll mainly be the TA for the Qatar students and also the Kigali students. So welcome to the course.
Okay, and so any of my other TAs who are here, I can't see all of your names over here. Can you just take turns and introduce yourselves?
Why don't you just join CMU Qatar?
Hi, I'm Kenora Ross now. I'm also located in Pittsburgh, and I'm looking forward to this semester. I'll find you guys either on Piazza or in my office hours. Have a good one.
Ethan. So Ethan's here. Some of my TAs are muted and they can't unmute, I guess. Anyway, so you'll meet the rest of them by and by. And I want to thank all of them even before the semester begins. Second, here's how this thing works. Keep yourselves muted at all times. You may ask questions, but when you ask questions, raise your hands first. This is just so that we have some.
Mama.
Oh, something happened. Somebody spoke, right? So make sure that you raise your hands before you speak. Keep yourself muted, and on the other hand, use chat freely. You can ask questions. The TAs are going to be here. They will answer questions on chat if I don't. I may not have time to actually go through the chat, but my TAs certainly will notify me of any questions that are mine to answer. And if they can answer anything, they will answer it too. And of course, you can discuss amongst yourselves as during the lecture. Now, let's begin with the actual material. If I can Yeah. So by now, all of you must have already watched lecture 0. If you have not done so, do so at once, because if you're not familiar with the logistics of the course, you're not going to go very far in the course. Hopefully, you've also looked at the homework 0. Homework 0 carries no points. Homework 0 is merely for you to get familiar with many of the things that we will use. And in particular, hopefully you've also looked at AWS and Google Colab. Hopefully you've been to the course website. If you haven't been there yet, please do so at once, because it has course objectives, logistics, quiz and homework policies, grading policies, everything over there. And we will be maintaining links to the lectures, slides, and the lecture videos and additional reading material. The course page will also have information about the latest deadlines, the homeworks, the quizzes, everything. So make sure to visit the page at least once a week, just to ensure that you've caught up with everything. And you should have already signed on to Piazza. If you haven't, do so at once. You must have verified that you have access to Canvas and AutoLab. Some of you might not. So if you don't have access to AutoLab, please notify us on Piazza and we'll set it up. And of course, you must have your AWS account set up. We've informed you that we are forming study groups. So, and this is highly recommended, because we believe that no matter how good a job we do, you learn best from your peers through discussion. You get only so much time from your instructor and from the teaching assistants. You have infinite time with your peers. So we highly recommend working in teams. All the cheating policies have been posted. So, as you might have seen from that, our policies are biased towards having you people collaborate rather than compete. We've also posted links to Google Docs where you can sign up, where you can list your study groups. So list your study groups. If you're not on any study group, we will assign you to study groups. So please enter your information as soon as you possibly can. All of the logistics for the study groups will be done by the end of this week. And I'm of course assuming that you have actually been through the logistics lecture. If you have not, you probably will not have many questions right now, because you don't know what I'm talking about. If you have, you might have some questions. So I'll wait for a few seconds for any questions that you might have. Questions, anyone about the logistics? Yes, no? I'm assuming not. So another point. Yeah.
Hi, Bhiksha.
So go ahead, Tushar.
Yeah, I have a question. So about the hidden slides. So will this be available after the class, after the lecture?
I was going to mention this. The slide deck, this actual slide deck has many more slides than what I present in class, because in class I try to keep it to what I can cover in 80 minutes. And in spite of my best efforts, these classes will often drag. Last semester, several of my lectures went on for 2 hours. It's unconscionable, but this was in spite of preparing all summer and trimming my material. It turns out that teaching over Zoom is just so much slower than doing it in a classroom. So I've trimmed it further this time to try to make sure that everything fits in 80 minutes. But that means a lot of the material in the slides is not going to be presented in class. They will be on the slides. The slides are on the course website, and the material in the hidden slides, which you can see in the PDFs on the course website, will turn up in the quizzes. So please download the slides and go through the slides quickly to make sure that you've also gone through the hidden material. Any other questions?
Yes, we have a question from Hoy.
Yeah.
Hello. I'd like to ask for the weekly quizzes. Is it timed? Is it timed, or can we just do it at our own pace?
You get 48 hours to do the quiz.
I I see.
It's open, right? It is not timed. I'm not interested in finding out how quick you are. I'm interested in finding out whether you got the subject. And this is the general policy that we have through the course. We have deadlines, we have rules. These are administrative necessities, but our final evaluation is intended to measure your skills rather than your discipline. And so it's largely skill-based or learning-based evaluation. Our idea is to find out whether you understood the subject. Your ability to do it within a fixed time frame is not something that's of great interest to us.
Okay, thank you.
Anything else? Okay, and one final note. Our course policy is that none of you gets left behind. What I mean is absolutely none of you. As far to the best of our ability, we will try to make sure that every one of you goes through this well and get grade. This doesn't mean that the evaluations are easy. The course doesn't get simple. Point, if you're having any kind of trouble, every one of you is going to be assigned a TA mentor. You can reach out to the mentor or you can reach out to me. Any trouble at all. Of course, if you're having problems with individual homeworks and quizzes, you can post on Piazza and go to office hours. If you have meta level problems with just getting stuck in the course, not being able to progress, worrying about how you're going to perform, or anything at that level of things, or just being afraid that you haven't understood enough and you're falling behind. Anything at that level of things, reach out to your mentors, reach out to me. We will do our very best to make sure that you do well. Again, if everything went as we would like it to, every one of you would get an A and you would earn it. Okay, so let's begin. Now, here is the topic of this course. We call it deep learning, but it's artificial neural networks, which have now become the main approach to AI. They have been successfully applied to various pattern recognition, prediction, and analysis problems. And in many of these, they have established the state of the art, often beating benchmarks set using earlier machine learning techniques by very large margins. And in some cases, they've even managed to solve problems that you simply could not solve using earlier methods. So here are some examples of breakthroughs using neural networks. Speech recognition. Researchers have been working on automatic speech recognition technologies since the 1950s. But after almost 65 years of research, the state of automatic speech recognition in 2015 was pretty miserable. Your typical speech recognition system was just made too many mistakes. And when people used applications like Siri, it was mostly as entertainment because it wasn't really that useful. It made so many mistakes. And then in mid-2016, we had this breakthrough. For the first time, speech recognition systems outperformed humans on a very challenging speech recognition task, the switchboard task, which consists of people calling up each other on the phone and talking freely about various topics. And this breakthrough was made possible by artificial neural networks. Since then, the technology has progressed in leaps and bounds, and today ASR systems generally outperform humans in speech recognition on most benchmarks. And of course, speech recognition has become a staple user interface, and this could not have happened without deep learning and neural networks. Same thing with machine translation. After 40 years of research, machine translation systems were pretty terrible around 2015. In October 2016, if you put an English sentence into Google Translate, which was one of the best translation systems at that time, and translated the English to Spanish, then took the Spanish and put it back into Google Translate and translated it back to English, the English that went in and the English that went out would not even be similar. It would just be often give you very absurd retranslations. Then in November 2016, something remarkable happened. Google Translate suddenly became really good. And the translations became very good overnight, literally overnight. And that's because in November 2016, Google switched over to using neural networks for translation. And the technology, of course, has continued to improve since then. And these days, automatic machine translation systems are better than even most human expert translators for most languages. In fact, these days, human translators will first put something into Google Translate and then correct what comes out rather than attempting to translate it entirely on their own. That's how good it has become. And this was made possible by neural networks. Image segmentation and recognition. Here's another one. So here, for example, is a very complicated image, and there are many objects in it. But then you'll note that all of the objects have been located, they have been segmented out, and they have been tagged with their labels. And this has all been done automatically with the neural network. So here, for example, you have a girl on a bicycle. So it finds the bicycle, it finds the human, it finds the backpack that she's carrying, all of them. And this level of detail, this level of performance is now routinely possible because we use deep neural networks for the job. But earlier machine learning techniques couldn't come anywhere close, just simply couldn't come anywhere close. Or here's another example. This one is a video, so let me see if I can pull it up. This is, let me see how this works. This is from a company called sighthound.com. They claim they can detect and identify cars on the highway. Very impressive. And of course, this is done using neural networks. And observe, here's a Kia Sportage, Hyundai Elantra. I mean, it's actually detecting every single car and recognizing the car. So when you get the white boxes, it has detected the car. When it becomes green, it recognizes the model. And it does so not just for cars, oncoming cars, but also for cars going away. It's very impressive. And this kind of performance, again, based entirely on neural networks. So you get the idea. It's these things have become really powerful. So again, here's another one. This is computer games. Now, for the longest time, it was assumed that the ultimate challenge in AI was playing games like chess or Go. And because these are essentially, these are not natural things. This is something that is purely, the playing of the game is purely a product of human intelligence. And so it was assumed that if a machine could have artificial intelligence, it must be able to do this as well as humans. And they didn't think it was possible. Then in the till the 1990s, chess games, automatic chess games, are a complete disaster. I don't know how many of you know this, but the first chess game that beat a grandmaster was built right here in CMU. This was Deep Thought by Feng Su, who did this for his PhD thesis in 89 or 90. And this game actually beat a grandmaster, although Gary Kasparov later beat it twice in 2 games. But then he went on to IBM, and they proceeded to build Deep Blue, which actually beat Gary Kasparov, the world champion at that time. And now, of course, even your PDA, the chess game on your smartphone can beat the world champion because they become so good. So fine, we've solved chess, but what about Go? Now, even after we managed to get automatic games that could beat the human champion in chess, Go remained an enigma. And that's because Go is vastly more complex than chess. While a chess game has about 10 raised to 120 possible states, Go has 10 raised to 180. So it's so much more complex. People assumed a computer could never beat a human. Then in 2016, AlphaGo beat the world champion. And after that, we have never looked back. Today, we have programs that don't even need to know the rules. They can begin exploring from scratch, figure out the rules, and just in a few hours, they can become good enough to beat the world champion, and that too is thanks entirely to deep neural networks. And or here's another one, image captioning. This one is actually old, from 2015 or 2016. And this technology is considerably improved since what we have on the screen here. I'm showing you this one to show you the sophistication of what was achieved suddenly when this first came out. So all of these captions are produced by a neural network. So here's this one, man in black shirt is playing a guitar. Construction worker in orange safety vest is working on road. Two young girls, well, this is not a young girl, but still two young girls are playing with a Lego toy. Boy is doing backflip on wakeboard. Very impressive. And all of these captions were produced by a network which only saw the image. So, and as you can see, these are stunningly accurate. Now, here's another one. These are all photographs of people that don't exist. This is a neural network getting creative, simply fantasizing faces from thin air. And this level of sophistication and creativity was not possible with earlier types of machine learning models. In fact, I don't think even humans can be this good at hallucinating up pictures, except the very best artists. So neural networks can paint imaginary faces, draw landscapes, generate music, write stories, and all of this has been achieved in just the past 4 or 5 years. It's very impressive. And many other such problems ranging from astronomy to healthcare to even stock prediction. In fact, neural networks are amongst the best performing models used by investment firms these days. So in fact, most investment firms have entire research teams devoted to neural networks. So you get the idea, right? Neural networks can do anything. If it's an AI task, the odds are that you can't beat a neural network model. You know, there's a common joke that the hardest thing for you to do is to rub your stomach in circles and pat your head at the same time. But if you built a model that could do it perfectly, it would probably be a neural network. So these things have defined AI. And last but not the least, these days, if you want any job in a data science or machine learning related area, having neural network expertise has become essential. It used to be a good skill that enhanced your resume 5 years ago. These days, not having it on your resume is a definite no-no. If you do not have neural network skills, then there are many jobs which are simply not open to you. So what are these magical neural networks that do all of these amazing things? So from where we stand at this point, there are these magical boxes where things go in and other useful things come out. For example, a voice signal goes in, a transcription comes out. Or an image goes in, a caption comes out. A game state goes in, the recommendation for the next move comes out. But then what's in these boxes? To understand that, let's begin here. All of the tasks that we just looked at, recognizing speech, captioning images, playing complicated games, all of these are fundamentally human activities powered by human intelligence. So perhaps the place to begin to understand how to do these automatically is by looking at the seat of all human intelligence, which is the human brain, or even earlier, even before the brain, to consider our amazing ability for cognition, our ability to think, to analyze, and to create. So, by the way, this picture epitomizes the notion of cognition. This is The Thinker by Augustin Rodin. This is something we do. Here are all of the magical things that we can do. Here are all the magical cognitive capacities we've got. We can learn. We can solve complex problems. We can recognize patterns. We can create. We can just sit in one spot and cogitate, think and reflect and imagine and dream without external stimulus. And these are the abilities that make us who we are. So if we want to build a machine with human-like capabilities, then these are the ones we must emulate. But then, how do we actually function? How does the brain perform all of these magical actions? Now, the problem with trying to understand this, who better to act to explain the issue here than Marvin Minsky, who stated it beautifully. If the brain was simple enough to be understood, we would be too simple to understand it. We just won't have the intelligence. A simple brain is not going to be very intelligent. We won't have the intelligence to know how it functions, but that doesn't stop us, right? So people have been curious about human cognition for thousands of years. In fact, the earliest models for it go back to at least the ancient Greeks. Is anybody in class familiar with this painting? Anybody? Just want to know. Raise your hand if you've ever seen this painting. I don't see anybody raising their hand. So 3, 4. So which one is it? Can you tell me? Anyone?
Aristotle.
So no, the painting, what is the name of the painting?
People are saying School of Athens. Athens in China.
The School of Athens, by a fire, right? And he actually painted this scene, and it shows all the scientific grades from Greek times till the 15th century. So you have Plato over here, you have Aristotle, I think there's Diogenes, Socrates, pretty much all of the grades. Anyway, so these guys, they too wondered about how the human brain works. So the earliest known model for cognition, it's called associationism. And that theory goes back at least to Plato, to 400 BC. And in fact, associationism was the primary model for human cognition until the early 20th century, with scientists such as David Hume and Ivan Pavlov developing theories around it. Associationism posits that the process of cognition is fundamentally one of learning. So what are associations? Lightning is generally followed by thunder. So we make associations between the two. And not just an association of the events, but also temporal association. So when you see a bolt of lightning, you expect to hear thunder shortly. If you hear thunder, you assume that a lightning just struck somewhere nearby. So these are associations. And of course, we're all very familiar with the most famous association experiment of all, Ivan Pavlov's dogs. How many of you are familiar with that experiment? Pavlov's dogs. Everybody must have heard of it, right? So what was it? Anyone remember? This is, by the way, guys, if you want to, yeah, exactly. So he trained a dog by ringing a bell and providing it food, and it learned to associate the two. Afterwards, every time he rang the bell, the dog would salivate. Anyway, so you have these theories, and the theory in general was that we think through the process of association, that we form association between percepts, and when we experience some, we sort of make the inferences, necessary inferences about which other percepts to expect. And it's a pretty good theory. In fact, it's most machine learning implicitly works off associations. But from the perspective of human cognition, the question still remains. Sure, we work off associations, but where are these associations stored in our brain? And there were several very strange theories on this for a very long time. But then things began to get more real once we learned about the structure of the brain itself. And this began with the invention of good microscopes, which got better from the 16th century onwards. And by the mid-1800s, people had figured out the structure of the brain, that the brain is essentially a large mass of a special kind of cell, namely neurons. Now, these neurons are all connected to one another. Each neuron has several incoming connections from other neurons, and each neuron connects out to several other neurons. So basically, the brain is a network of neurons. And there has to be something about this network that enables cognition and the inferences that we make. Now, still not clear how this is done. The first person to realize how things worked was this guy, Alexander Bain, back in the 1870s. Like all the scientists of the day back then, Bain was a bit of everything. He was a philosopher, he was a psychologist, he was a mathematician, a logician, a linguist, and he was a professor. In those days, it was much harder to be a professor. In his 1873 book, Mind and Body, Bain postulated that the brain stores information through its connections. He postulated that the brain stores all of its information regarding associations between percepts, or more generally between stimulus and responses, through the structure of the connections between the neurons. In fact, this was the first connectionist model. And he even came up with various computational models for his theory. The key idea here was that the same connections, if appropriately arranged, could result in different outputs for different inputs. Now, this may seem obvious to us today, but in Bain's time, this was some kind of a heresy. People just didn't believe it. So here's one of his circuits. It assumes that all inputs and all outputs are binary, and a neuron fires if all of its inputs fire. So over here, we can see that if A and B are both 1, then X fires. If A and C are 1, Z fires. If B and C are 1, Y fires. If all are 1, all of them will fire. So although you have a single circuit, for different input patterns, you get different firing patterns for the output. And not only this, Bain even included models where a circuit's output could depend on the intensity of the input. For example, here, if the input is low intensity, then Y, which receives 3 copies of the input, will fire, but X will not fire. Whereas if the input is high intensity, both X and Y will fire. So, and these are actually modern network models. But Bain came up with these in 1873, 150 years ago. These models have been around for that long. And he not only showed the circuit structures, he also proposed a learning mechanism whereby the brain, or any computational model of it, could learn these connections. And here's Bain's proposed mechanism for how neuronal connections could be learned. So in his own words, when 2 impressions concur or closely succeed one another, the nerve currents find some bridge or place of continuity that reverse according to the abundance of nerve matter available for the transition. So it sounds very complicated, but basically he was predicting Hebbian learning, which we will see in a few minutes. And he did this 3/4 of a century before Donald Hebb. Very impressive. But then, sadly, Bain's peers in the 19th century thought he was full of it. He thought he was speaking nonsense because all of this was so outlandish. And eventually, even he began doubting himself. To quote the famous mathematician and philosopher Bertrand Russell, the fundamental cause of the trouble is that in the modern world, the stupid are cocksure while the intelligent are full of doubt, and Bain doubted himself. So in 1873, Bain postulated that there must be 1 million neurons and 5 billion connections to capture about 200,000 percepts. This seemed like a very large number. Then by 1883, he realized that he hadn't taken into account partially formed associations. In the process of forming an association, there are a lot of partial, during the process of learning, there are many intermediate stages. And his computation for how many neurons and connections you would need had not accounted for this. And the more he thought about it, the more implausible it seemed. By 1903, he decided that our brain is simply not large enough, that his model was broken. It would need too many neurons and too many connections for his model to work. And so just before he died, he recanted all of his ideas, which is sad because he was right in 1873 and wrong at the end. It turns out our brain is very, very large. Does anybody have any idea of how many neurons we have in the brain? Anyone? Someone want to take a guess? So 80 billion. So yes, Ali is right. The actual number is 80 billion, which is a large number. How many connections do we have between neurons? Anyone? Anyone want to take a guess? It's 100 trillion. That's how many connections we have. It's that little thing you have above your neck. It's got 100 trillion connections between neurons. It's enormous. It's more than enough for Bain's theory to hold, and it does hold. So connectionism lives on. We know by now that our brain is a connectionist machine, as predicted by Bain in 1873, and this guy David Ferrier in 1876 in his book, The Functions of the Brain. The way it works, your brain is a mass of neurons. Neurons connect to other neurons. And the processing and information capacity of the brain is a function of these connections. So modern artificial neural networks are connectionist machines, which emulate this architecture. And so this is what a connectionist machine is. It's a network of simple processing elements where all world knowledge about the task that the machine performs is stored in the connections between the elements. And so all modern neural networks are connectionist machines with many little processing units connected to one another. Not quite like this, but this captures the idea. Now, does anybody know what type of architecture your standard computer has? Anyone? So what's the architecture? Some of you must have worked on computer architecture. So what's the? That's right, right? As a von Neumann architecture. Actually, von Neumann. What is the specialty of the von Neumann architecture? By the way, if you want to speak, just hit your space bar. How does it work? That's right, right? So you have a processor, and then you have the memory, and these two are separate. So the program and the data live in memory, and the processor is separate. That was von Neumann's original architecture. We actually have various variants of it. So you have, for example, the Harvard architecture, where you have separate memories for data and programs. Whereas in the original von Neumann architecture, the data and programs are all in the same memory. And modern machines use a hybrid approach. The processor core is Harvard, where you have separate memory for the programs and data. But the main memory is Princeton, which are von Neumann, where data and programs all live in the same space. Now, the difference between the Princeton, the von Neumann, and the Harvard architecture is not so important. What is important is the form of the architecture. The processor is separated from the memory, which holds the program and the data. So if you want to run a new program, all you have to do is change what is in the memory. You just upload a new program into the memory and you're set to go, which is why your typical computer, even your smartphone, is able to do so many different things. In order to make it perform a new task, you only have to load the corresponding program into the memory and you're set to go. With connectionist machines, this is not the case. For connectionist machines, the computer is the program because the program and its memory are all encoded in the connections between the units. So to change the program, you have to change the machine itself, which is why we usually emulate connectionist machines on regular Princeton or Harvard architecture machines. And very rarely do we actually go off and build a new connectionist machine in silicon when we want to perform a task. I mean, it would be a very highly ineffective thing to do. And so a quick recap for all we've seen so far. Neural network-based AI has taken over most AI tasks. Neural networks originally began as computational models of the brain, or more generally, of models of cognition. The earliest model of cognition was associationism, and more recent models of the brain are connectionist, where neurons connect to neurons and the workings of the brain are encoded in these connections. And current neural network models are connectionist machines. So we have a quiz now. We will periodically have polls through the lecture, through every lecture. This is just to make sure that I can keep track of whether you guys are, following what I'm saying and whether you understood the concepts. Okay, guys, you have 5 seconds. All right, I'll stop the polling. But yeah, the first person to propose connectionism was Alex Bain, and there are 100 trillion connections between neurons and the brain. So for those of you who could not see the poll, I should probably pull up the poll. Anyway. So here we are. Connectionist machines. Well, here, so quick recap. Connectionist machines are networks of processing elements where all the information used to perform the computations is in the connections, and these individual processing units themselves are very simple. But what are these units? So to understand what the units are, let's go back to the brain. In the brain, the individual units are neurons. A neuron looks roughly like this. It has a head called the soma, within which the nucleus resides. The soma has several dendrites through which it receives signals from other neurons. The neuron generates signals that are spike trains, the rate of which depends on the total input signal. At a high level, roughly speaking, we can think of it this way. If the total input signal from the other neurons exceeds a threshold, the neuron fires. The output of the neuron goes down this long leg called the axon, from which it's transmitted to other neurons. And here's an interesting little factoid. This axon can be very long. It can, in fact, be the length of your entire leg. So this needs to be protected for the neuron to work. And to protect it, it's covered with a sheath of fat called the myelin sheath, which are produced by something called glial cells. And this fat is crucial for the functioning of the brain. In fact, they stored Einstein's brain and they studied it, and they found that what was different between Einstein's brain and normal brains was that he had many more glial cells, the cells that produce this fat, the myelin sheath, as it's called. Einstein had much more of it than normal people. It turns out that the more fat you have in your head, the smarter you are. So in fact, being called a fat head, it's actually a compliment. Now, here's another factoid that may only interest me. Neurons don't actually undergo cell division, unlike the other cells in your body. Neurons are created from neural stem cells. And this creation of new neurons goes down to almost zero just shortly after you're born. In other words, you're born with pretty much almost all the brain you're ever going to have. Anyway, for our computational connectionist models too, we are going to use units which emulate the operations of biological neurons. The first computational model for the neurons for the neuron was proposed by these two guys, Warren McCulloch and Walter Pitts. Warren McCulloch was a neurophysicist in the University of Chicago, and Walter Pitts was a homeless guy who knocked on his door. So anybody want to take a guess as to which of these two is Pitts and which is McCulloch? If you think the one to the left is Pitts, raise your hand. Yeah, most people seem to think it's a guy to the right. Yeah. Anyway, this is Warren McCulloch. He liked his wine, obviously. And Pitts was like a teenage kid who had run away from a home and ended up in Warren McCulloch's door. And McCulloch, put him up at home, and they worked on this model, which is published in 1943, a logical calculus of the ideas immanent in nervous activity. And when they actually published this paper, which is probably the most famous paper in neuroscience and also AI, as in terms of being foundational, Pitts was only 20 years old. And at that point, I don't think he even had a high school education. So this picture on top, that's a pictorial visualization of the model. Now, the actual neuron over here is shown by this triangle. The line going out represents the outgoing signal. The colored lines, they represent incoming signals. There are two types of, and they are connected to the neuron through these little connections, which are called synapses, fashioned after the neurons in the brain itself. Now, there are two types of synapses in this model: the excitatory synapses and the inhibitory synapse. Now, the excitatory synapse transmits weighted inputs into the neuron. So the number of connections from the incoming line represents the weight. Here, the weight of this connection is 2. The inhibitory synapse has the property of basically killing the activity in the neuron. So if there's any signal coming up this line, then the output of the neuron is going to be 0, regardless of what comes in through the other lines. Now, by appropriate choice of excitatory and inhibitory synapses, McCulloch and Pitts, the McCulloch and Pitts neuron can be made to emulate any Boolean gate. So here are in the top left, when neuron 1 fires, then 1 time later, neuron 2 copies are firing. And in each case, the neuron fires if the total input is so 1 fires, 1 instant later, 2 gets inputs. So this is a simple delay. Now this one, if 1 fires, then this is going to get 2 inputs. If 2 fires, then 2, this is going to get 2 inputs. So if either 1 or 2 fire, this will fire. So 3 is 1 or 2. Here, for 3 to get 2 inputs, both 1 and 2 must fire. So 3 is 1 and 2. Now here, if 1 fires, 3 gets 2 copies of it, so it could fire, but then it's also dependent on 2. 3 cannot fire if 2 is active because 2 has a inhibitory connection. So this is 1 and not 2. And once you can begin constructing these basic gates, you can construct any Boolean circuit at all using these neurons. And in fact, McCulloch and Pitts showed you can even produce much more complex responses. For example, this circuit over here, it models temperature response. Again, every line has a delay of 1. So it has 2 inputs, a heat receptor and a cold receptor. Now the blue unit, this is just a delay, meaning whenever you have 2 outputs a value, 1 time instant later, this guy is going to output the same value. The red one is a little more complex. The red one over here has an excitatory signal to blue, but it has an inhibitory signal to the cold receptor. So if, let's say, the cold receptor fires at time t equals 1. Then at the next instant, this guy gets 1 input. And this guy gets 1 input, but this guy has not yet fired, right? So when the cold receptor fires once, the cold sensation gets only 1 input. And so you don't feel cold. For the cold sensation to work, the cold receptor must fire twice. The cold receptor must persist for at least 2 time instants. That way, after 1 time instant, you're going to get this input. But then you get this again at the 2nd time instant. And at the 2nd time instant, you get the delayed signal from the 1st time instant through this line. And so you're going to sense cold. So when you have an extended cold input, you sense cold. What happens when you have a very short, very brief cold signal? Then this guy is never going to fire, because this only fires when you have an extended cold input. Say you have a cold input. So after 1 time instant, this guy fires. After 2 time instants, this guy gets this one's input, but the cold receptor has gone quiet, right? So the only input it gets from here, so the red one fires. And then shortly later, the heat sensation fires. So you have this interesting circuit where extended cold signal will only give you a cold sensation, but a very brief cold signal will actually give you a sensation of heat, which is basically how even the human body functions. So they were able to compose these complex, almost biological behavior using these neurons. Now, of course, the model was not without criticisms. Clearly, the McCulloch and Pitts model was very powerful, but then they overstated it. They claimed that their networks could compute a small class of functions, which was true. But they also claimed that if you provided the network with tapes, the networks would become Turing machines that could solve any problem that a Turing machine could solve. This, of course, is easily seen to be false because these are finite state machines and they can't be Turing complete. Also, they didn't actually prove any results. They just made claims. And last but not the least, they showed you how networks built of such units could do various things, but they didn't provide any learning mechanism whereby the network could learn its connection patterns from experience, from data. For that, we had to wait for another guy, this man, Donald Hebb. Hebb was another interesting character. He was a Canadian, and initially he trained to be a novelist. Then he wanted to be a farmer. Then he wanted to be a hobo. Then he figured he'd be a school teacher. And then after having gone through all of that, he eventually decided he wanted to be a psychologist and got a PhD from Harvard. It's quite a career. And then went on to work at a variety of places. Now, in 1949, he published a book titled Organization of Behavior, where he outlined a mechanism whereby neuronal cells in the brain could learn their connection from data. Here's how he described the mechanism. When an active cell after cytosine and repeatedly or persistently takes part in firing it, some growth process or metabolic change takes place in one or both cells, such that A's efficiency as one of the cells firing B is increased. Again, this is very complex as it is stated, but what it's essentially saying is that if you have 2 neurons A and B close to one another, as A repeatedly excites B, its ability to excite B improves. So this is often stated like so: neurons that fire together wire together. So here's Hebb's model for how neuronal learning happens at neuronal connections. Let's look at one connection between 2 neurons. Let's call them, say, X and Y. So these are 2 neurons. Now, neuron X connects to neuron Y at a synapse. At the synapse, the axonal connection from neuron X has a knob called the synaptic knob, through which it connects to the dendrite of neuron Y. It isn't actually a physical connection. The actual signal transfer happens through chemicals called neurotransmitters that flow from the synaptic knob of X into the dendrite of Y. every time a signal from X successfully triggers a response from Y, then this synaptic knob gets slightly larger, making it easier for X to trigger Y the next time around. So so every time X successfully triggers Y, the strength of the connection increases. This was Hebbian learning, and it can be formulated, it could be stated formulaically like so. Let WXY be the weight of the connection between neurons X and Y. Then, the neurons are both binary. They can take the values, X and Y can take the values 0 or 1. Then the Hebbian learning rule says that after each time these two interact, after each signal that goes down through this guy, WXY is going to be WXY plus eta times XY, meaning every time both of these guys become 1 at the same time, meaning every time X successfully excites Y, the strength of the connection is going to increase. And this is the famous Hebbian rule. Memorize it. We're going to keep seeing it again and again. That every time when two neurons are connected, every time both of them become 1 simultaneously, the strength of the connection increases. It's the basis of many learning algorithms, but then there's something problematic with this model. And what is that? Can anybody tell me what the issue with this might be? Anyone? Anybody want to guess? What could be the issue with this? The weight always increases, right? That's exactly it. No way to decrease intensity. So it's fundamentally unstable. The weights can never decrease. So over time, eventually all the weights, if you wait long enough, all the weights will become large. The entire net model is just going to have saturated weights and become useless. So we need ways to decrease the weight, and various proposals have been made for how to modify it, allowing for weights to be normalized, forgotten, etc. For example, this is Sanger's rule, generalized Hebbian learning, where an input xi is allowed to contribute to many outputs. So basically saying a neuron can connect to multiple other neurons. But in order to determine how much the weight between an input and a particular output must be updated using the Hebbian rule, we subtract out the contribution for any particular output, we subtract out the contribution of that input to those outputs. I mean, it's an interesting variant, but this was just one of many that came out. However, the best and most lasting update to the Hebbian rule came with the introduction of a new model. But before I go to that model, we have the second poll. So can we pull up the second poll, please? Yeah. This was easy, right? I'm not sure why we got a few blues for the other bars, but if you've been paying attention these past few minutes, the fact is, as it states right here on the slide, Hebbian learning is fundamentally unstable because there's no reduction of weights. So we need a better model. And that model came from this guy, Frank Rosenblatt. This is Frank Rosenblatt. He was a logician at Yale, and in 1958, he proposed a neural model called the Perceptron, which which took the world by storm. And at that point, it was Rosenblatt and much of the world was convinced that this is going to solve all AI problems. Now, his actual model was quite complex. It's on the slides, take a look. But here's the simplified version of his original proposal. This is each neuron over here. This is the perceptron, receives several inputs. So these in the figure, these inputs are xi through x1 through xn. This neuron receives n inputs. The neuron computes a weighted sum of all of these inputs. This weighted sum is compared to a threshold. If the weighted sum exceeds the threshold, the neuron fires. Otherwise, it does not. So if I were to write it in math, this is what it would look like. If the weighted sum of all of the inputs minus the threshold is greater than 0, which is the same as saying if the weighted sum of the inputs is greater than the threshold, the output is 1. Otherwise, it's 0. So electrical engineers amongst you will recognize this as threshold logic. Now, Rosenblatt originally imagined that with appropriate choice of weights, this model could represent any Boolean function and perform any logic. And we'll see in the next class why he was so easily fooled. And the popular media of the time even bought into the hype. So here are some snippets from a couple of newspapers of that time. The embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. This is the New York Times, 1958. Frankenstein monster designed by Navy that thinks. Tulsa, Oklahoma Times, 1958. I mean, this was the hype. And Rosenblatt not only came up with the model, he even came up with a beautiful learning algorithm through which you could use to learn the weights of the connections to perform any Boolean task. So let's say you have an input X and an output Y, then and let W be the connection, weight of the connection between X and Y. Then each time you get an input and you get a corresponding output, the weight is updated using this very simple rule. It's very similar to Hebbian learning. So W equals W plus eta times D of X minus Yx times X. Now, what is D of X and what is Y of X? Y of X is the actual output in response to X. D of X is what you want the output of the neuron to be. Remember, you're speaking of learning. So you have a desired output for the neuron. So this looks a lot like Hebbian learning, except in the case of Hebbian learning, you just had Y times X. So the weight incremented in proportion to the product of the input and the output. Whereas here, if the neuron is already doing the correct thing, then there is no more correction to be made. But if the neuron is making an error, then there is a correction that's proportional to the error, the difference between the target output and the desired output. And so this is the famous perceptron learning rule. And Rosenblatt, and you can actually show that when you're trying to distinguish between classes that are linearly separable, meaning you can draw a hyperplane in some high dimensional space which separates the classes, then this rule will actually learn that hyperplane. So you not only have a model, you have a learning algorithm. And sure enough, it's relatively easy to see how the perceptron can mimic any Boolean function. So consider these examples. In these figures, the number written on top of each arrow shows the weight of a connection, and the number in the circle represents the threshold. So in the top left figure, X has a weight of 1, Y has a weight of 1, the threshold is 2. So the only way the total input is going to match the threshold is if both X and Y are 1. So this output is X and Y. Here, the threshold is 1. So if either X or Y are 1, the total input is going to be 1, which matches the threshold. So this is X or Y. Here, the threshold is 0, but the weight is minus 1. So if X is 1, the input that comes in becomes minus 1, and this will not fire. But if X is 0, the input that comes in is 0, it's going to match the threshold, and this will fire. So this is not X. And so you can see that you can clearly, this perceptron can model any simple Boolean gate, which means it can model any simple Boolean function. But then Minsky and Papert blew a hole through all the hype when they showed that while it can model simple Boolean gates, there is no setting of the weights for which this unit can compute the XOR. It can never compute X XOR Y. And we'll see how this is true later. But in any case, this means that the perceptron is not a universal Boolean machine. It cannot do everything. And this discovery caused so much dismay in the scientific community that research funding into perceptrons and neural networks basically dried up for many years. And so to resolve this problem, we have to go back to the brain. A brain is not just a single neuron. The brain is actually, as we saw, a network of neurons. So for our computational model 2, although individual perceptrons are other weak computational elements, you can greatly extend what you can do with them once you begin networking many of them. So in order to perform complex computations like the XOR, you will need to connect multiple of these perceptrons. If you just connect up 3 perceptrons, for example, you can compute XOR as is shown in this figure. Here we've connected these perceptrons in a layered manner. We have 2 perceptrons in the first layer, and then we have a third perceptron which operates on the outputs of the first 2 perceptrons. This first perceptron computes X or Y. The second perceptron computes not X or not Y. And the third perceptron ANDs the 2 outputs, which gives you X or Y. Now there's some terminology over here. This first layer of perceptrons is what we'll call a hidden layer. It is hidden because you don't actually see their outputs directly. They are hidden from you. You only see the output of this final neuron, which we call the output neuron. This entire layered structure network of perceptrons is what we call a multi-layer perceptron or an MLP. And once you realize that you can begin connecting up perceptrons into a network to compute more complex Boolean functions, then you realize that you can indeed compute arbitrarily complex Boolean functions simply by connecting up perceptrons in the right way. So in cognitive terms, we can compute arbitrary Boolean functions of sensory input. So for example, this ugly looking network over here operates on 4 inputs and computes this absurd looking function on top. A network of perceptrons can indeed be a universal model for Boolean functions. And so here is the story so far. Neural networks began as computational models of the brain. They are connectionist machines. They comprise networks of neural units. The McCulloch and Pitts model model neurons as Boolean threshold units, and they model the brain as performing propositional logic, but they gave us no learning rule. Hebb's learning rule was that neurons that fire together, wire together, this turned out to be unstable. Rosenblatt's perceptron was a variant of the McCulloch and Pitt neuron with a provably convergent learning rule, but individual new perceptrons, it turned out, are limited in their capacity. Multi-layer perceptrons can model arbitrarily complex Boolean functions. So we can, but then our brain is not Boolean, right? We don't receive only Boolean inputs and make only Boolean inferences. We operate on real valued inputs and make non-Boolean inferences. So how does this perceptron and the multi-layer perceptron square with all of that? For that, first, let's consider real valued inputs and Boolean outputs. So here now the inputs x1 through xn, they are all real values. These weights, they too are real values. And the perceptron fires if the weighted sum of inputs exceeds the threshold. So in math, we say the output of the perceptron is 1 if the weighted sum of the inputs minus the threshold is greater than or equal to 0. Otherwise the output is 0. So I can see the model slightly differently. Instead of comparing the weighted sum of the inputs to a threshold, we can say the perceptron applies a threshold activation to an affine function of the inputs. An affine function is a weighted sum of the inputs plus a bias. And so this threshold activation is a function which outputs a 1 if its argument is greater than or equal to 0, and it's 0 otherwise. Now this is just rewriting the same model as before. In fact, if you set the bias to be equal to minus t, then this is the same as this model over here. Now, but now, once we write it this way, we can also extend the perceptron to have real valued outputs. Instead of applying a threshold activation to this affine function of the inputs, we can replace it with a sigmoid, which goes smoothly from 0 to 1, rather than jumping from 0 to 1 suddenly when this value exceeds a threshold, or when this value exceeds 0. Or we can, in fact, replace that activation with any real valued activation, any real valued function that operates on an affine function of the inputs. And we'll see many of these activation functions later. The result here is that now the perceptron will be mapping real valued inputs to real valued outputs. For the purpose of building our intuition and interpretability though, I'm going to continue to assume real valued inputs, but Boolean outputs. So, and I'm going to continue to assume a threshold activation over here for purposes of explanation. We will visit the other types of activation functions later in the next class. So here is our real valued perceptron again. You're computing a weighted sum of the inputs. If that exceeds a threshold, the output is 1, otherwise it's 0. So this means that in the input space, there is some combination of the inputs which where the output is going to be 1, and the other combinations where the output is going to be 0. And the boundary between these two combinations is going to be where this weighted sum is exactly equal to this threshold. That is the equation for a hyperplane. In 2 dimensions, it's the equation for a line. So this is how the perceptron is going to behave. There is a hyperplane. For all inputs on one side of the hyperplane, the output is 1. For inputs on the other side, the output is 0. For this 2-dimensional case, if I were to draw it in 3D, this is the function that's captured by the perceptron. There is a line, and for all inputs on one side of the line, the output is going to be 0. At the line, the output jumps up, and then it becomes 1. So you're going to get this step function. Now, once we see how this perceptron actually operates on reals, we can see how it models different Boolean functions. Now, for Boolean functions, the inputs are all binary. So if you had 2 inputs, the inputs are going to be either 0, 0, 1, 0, 1, 1, or 0, 1. Now, if your perceptron has a threshold, which is given by this line, then it's going to fire for these 3 combinations of inputs. And so this perceptron fires when any of the inputs is 1. This perceptron is clearly an OR. For Boolean inputs, what is this perceptron? Anyone? What would this one be? That's an AND, right? It only fires when both inputs are 1. And what is this? It's not an XOR. You cannot do an XOR with a single perceptron. Remember? It's ignoring X2. It's inverting X1. This is just not X1. Exactly, right? So you see how, although we kept thinking of it in terms of threshold logic and so on, this explanation actually completely explains its Boolean behavior. But it can also you can also think of it as a function in real valued space. And now we can see how we can compose more complex decision boundaries. For example, consider this. In 2 dimensions, I want a network that's going to I want a multi-layer perceptron that's going to output a 1 if the input is inside this pentagon and it's 0 outside. It's very easy for me to construct it. Here's what I'd do. I'd first have one perceptron, which captures this low boundary. It's going to output a 0 for all inputs over here. It's going to output a 1 for all inputs in the yellow region. Then I can add a perceptron for this boundary, which is the second one. This is going to output a 0 over here, and 1 over here. A third perceptron for this boundary. A fourth one for this guy. A fifth one for this guy. And so now, having got all 5 of these, if I consider this pentagon is the only region where all 5 of these perceptrons fire. I sum all their outputs. Their sum is going to be 5 inside the pentagon, and outside the pentagon, at least one of these perceptrons is not firing. So the sum is going to be less than 5. So now I can just have a little AND gate over here, which is also a perceptron, where all the weights are 1 and the threshold is 5. And this one is going to only fire when all of the inputs, when all of the first layer perceptrons output a 1, which is when the input lies inside this pentagon. And so this overall network is now going to output a 1 when the input is inside the pentagon and 0 outside. So did everybody get this? If this didn't make sense, raise your hands. Okay, everybody got it, right? Yes. Okay, Joe, what was the question? You can use your space bar to ask a question. So I guess no question. All right. So now once you can compose this pentagon, right? This is very easy to see how it happens. You can compose more complex decision boundaries like this one. For example, let's say I want to have a network which outputs a 1 if the input is within either of anywhere in this yellow region, but 0 if it's outside. Here's what I will do. I will use one subnet to output a 1 when the input is in the lower pentagon. I'll create another subnet to output a 1 when the input is in the higher pentagon. I'll have a final neuron which performs an OR of the two. And this one's going to fire if either this one fires or this one fires. And you can see how this guy is now going to fire. This entire network is going to fire if the input is in either of these pentagons. And it's going to output a 0 otherwise. And once you figure out how to do something of that kind, then you can construct even more complex decision boundaries, like this strange figure to this left, or this some decision boundary for a human or a horse. And it should be easy for you to figure it out, think about it. We'll see it again in the next class. And so now we know how to build a multi-layer perceptron for complex classification tasks. Your input is going to be, so let's say you're performing a digit classification over images. So your input is going to be a picture of this kind. This is from MNIST. Here the image has 784. So your input lives in a 784 dimensional space. In that 784 dimensional space, all the digits that are 2 live within some region of the space that you can close off, which is sort of illustrated by this peanut-shaped figure. And so now all you need to do is to compose a network which will output a 1 if the input is inside this peanut, and output a 0 if it's outside. And voila, you have a 2 classifier. So, and you can build this kind of network using the principles that we just saw. So here's the story so far. MLPs are connectionist computational models. We saw this. Individual perceptrons are computational equivalents of neurons, and MLP is a layered composition of many perceptrons. They can model Boolean functions. Individual perceptrons act as Boolean gates, and networks of perceptrons are Boolean functions. MLPs are multi-layer perceptron, right? So the MLPs are Boolean machines. They represent Boolean functions over. They represent Boolean functions over linear boundaries. So this is the key piece. Observe how we did this. We constructed each of these neurons basically only composed a linear boundary. So the first layer neurons, all perceptrons, which I will sometimes also call neurons, captured linear boundaries. And the rest of the network simply composed a Boolean function over the linear boundary. So this one said, is the input within all of these boundaries? This one said, is the input within all of these boundaries? This neuron said, are both of these guys firing? And you got the more complex decision boundary, right? So what happened? Someone scribbled here. I hope we are not being Zoom bound. So these things can represent arbitrary decision boundaries, and they can be used to classify data. By the way, guys, if anybody is trying to scribble on these things, please don't. It can get very disconcerting. I don't think I've been particularly careful about keeping this secure. So we've seen that, okay, there is a oh yeah. All right, the correct answer is 7. You're going to need 6 perceptrons for each of the 6 sides of the hexagon, but then you need the final but then you need the final perceptron which ends the output of these 6 perceptrons. So the actual answer is 7. 6 for the sides of the perceptron and 7 for the final end, right? So far we've seen networks that produce Boolean or even categorical outputs, but what about real valued outputs? We've already seen that we can have perceptrons with real valued outputs, but can we use networks of these kind of this kind of neurons to say construct a function of this kind? And the answer is yes. To see how this is done, this can be done, let's consider a function of a scalar input. So here I can have 2 perceptrons, one of which outputs a 1 when the input exceeds threshold T1. The second one outputs 1 when the input exceeds T2. And this guy combines the outputs of these 2 perceptrons with weights 1 and -1. So let's see how the overall thing behaves. As you increase the input, when the input exceeds T1, assume T1 is smaller than T2. When the input exceeds T1, this guy fires, but this guy has still not fired. So now before T1, neither of these 2 guys fire, so the output is 0. When the input is greater than T1, this one fires, but this one doesn't fire. So you get these 2 guys coming in and the output is going to be, you get a 1 from here and a 0 from here, so the output is going to be 1. When the input also exceeds T2, both of these 2 guys fire. But because they have weights 1 and -1, they cancel out. And so the output is going to be a 1 between T1 and T2 and a 0 everywhere else. And you can specify T1 and T2 anyhow. But once you can construct that, you can use networks of this kind to compose a complex function like this blue curve. you can just say, all you would have to do is to partition the x-axis into ranges and use one subset of 2 neurons for each portion of the range. And so that's going to give you a unit step function within that range. You can scale the outputs of each pair of neurons to the appropriate height and sum them up. And when you do that, you end up approximating this function by the outline of this red curve. And you can make this approximation. We'll address the question about layers in the next class. So you can make this approximation arbitrarily precise by making these ranges narrower and narrower and narrower, and filling more and more of this axis with these ranges. So in other words, you can approximate even continuous valued functions to arbitrary precision. So here's the story so far. Here is everything we've seen so far. The new fact we've learned is that MLPs can also model continuous valued functions. So, yes, here's the last poll. Ten seconds, guys. All right, let me stop. So one, the answer is one, because the activation function is sine. I basically gave you the same function that you're trying to model. So this was a bit of a trick question. I've been using threshold functions as to explain things, but if you change the activation function, you can model more complex functions with a smaller number of perceptrons. So anyway, so here are other things MLPs can do. In addition to the various things we saw so far, they can model memory. If you connect networks, neurons in the ones that neural networks we've seen so far, the information flows from one end to the other. But if the neurons are connected in a loop, they can model memory. They can model represent probability distributions over integer domains, over real valued domains, over complex valued domains. They can model a posteriori and a priori probability distributions of data. They can even generate data from complicated or unknown distributions. And yeah, they can, that last one I'm being facetious. So, by the way, the sigmoid is going to give you between 0 and 1, not -1 and 1. We'll discuss those issues in the next class. So going back to our problem, from our AI perspective, a neural network is just a function. Given one or more inputs, it computes the function to predict one or more outputs. And so in all of these tasks, these boxes take in an input and produce an output. What kind of machine takes an input and produces an output? It's a function. And so these boxes are all just functions which take in the voice signal and produce the transcription, image and the caption, the game state and the next move, and so on. And these functions are modeled using neural networks, or approximated using neural networks. And so to close for today, multi-layer perceptrons are connectionist computational models. They are classification engines. They can model continuous valued functions. Interesting AI tasks are functions that can be modeled by the network. Now, we've just sort of established that neural networks can model any odd kind of function. They can model Boolean functions. They can model category functions where they operate on real valued inputs and produce categorical outputs, like 1 if the input lies in some region of the space and 0 otherwise. Or they can even produce continuous valued functions. Now, exactly how we will do this, so they are universal approximators. We will discuss more about this in the next class. And the issue of depth has come up several times during this lecture. So we'll also discuss the issue of depth in detail in the next class. I'll stop right here. We have a minute for questions. Any questions, guys? You can unmute yourself. Questions, anyone?
Professor?
Can I ask a quick question? Oh, sorry.
Okay, go.
Oh, you go first.
Okay, go ahead.
All right. So, like, I just want to ask, like, if the poll is based on participation or correctness, like, for counting towards the, like, participation grade.
I'm not scoring you for the polls again. So please don't answer the polls because you expect to get points for it. We will tell you how frequently you're right, but the poll informs me and you whether you have been following and whether you understood what was said. If 80% of you get something wrong, then obviously, you know, I either put you to sleep or didn't explain it properly, right?
Right. Thank you. I'm just, yeah.
Your participation is extremely important. So please answer the polls. I depend on you.
All right. Thank you very much.
Yeah. Gui, what was your
Professor?
question? Yeah.
Can you please explain the last question? I mean, the question in the last poll, please?
Fine. So here, all we did over here in the last poll was that we replaced this. Let me go back to my neuron over here. I replaced this activation function theta by sine of z. Right. So when I replace this with sine of z, then basically z is simply going to be x plus pi over 2, which gives you cos of z, or 2x plus pi over 2, right? Which gives you cos of z.
Oh, yeah. Oh,
right?
Yeah, I see.
Any other questions, guys? Okay, fine. We are over time. Thank you all. And once again, welcome to the course. I have confidence that all of you will do well. It will be a fun course. It will be a lot of work, but you know, we take it upon ourselves to make sure that all of you succeed in the course. So take advantage of all of the help and the various resources we will provide, and don't be afraid to reach out. Good luck and thanks again.